So how are we going to read a titration curve? That's what we are going to explain. And now in the titration curve, as I have shown here, you can see 4 different titration curves here, right? So which is which and what is it represents? How can you read is very easy if you pay attention to some details here. So if you have a titration curve that looks like in the first one here, they may not be giving you all these details, okay? So in this case, what you can do is you can read the pH on the y-axis, and also you can see what is on the x-axis, right? X-axis is normally volume added. Remember when you were doing the titration, you just entered volume for the x-axis. So we don't know what is it acid or base added, correct? So just by looking at the curve, we can say which one is added from the burette. So whatever is on the x-axis is coming from the burette. Does that make sense? Okay, so that is from the burette. And whatever is at 0, that means you haven't added anything from the burette. That means we started with a flask, Erlenmeyer flask with something in it, right? So that is what is indicated at 0. So in the Erlenmeyer flask, since the pH is here, see this pH is, this is 2, so we can say that is very close to 1, correct? If it is very close to 1, the pH 1 is nothing but strong acid. So we can say that is a strong acid, pH 1. So just by looking at the curve, we can say that is a strong acid in the flask. And now when you look at the curve, you can see that when you keep adding something from the burette, the pH is going up, and finally we reach to a point where it is almost closer to 14. And we know pH 14 is nothing but a strong base. Okay, so we know that from the burette, strong base is added. So we know that is a strong acid, strong base titration. More accurate way to determine whether it is a strong acid, strong base titration is by looking at the equivalence point. So when you look at this vertical part of this titration curve and take the mid part of that one, if that is coinciding with a 7 on the y-axis, when you extend that one back to the y-axis, and if it is on 7, we can say that is strong acid, strong base titration. Okay, and now how can we decide? By looking at the graph here, the third one, okay, this is second one, this is the third one I'm going to explain. So the third one, if you look at this one, you can see that something is added from the burette and the pH is, final pH is around 1 here, and when the volume on the x-axis is 0, the pH is 13. Correct? So if the volume from the burette is 0 means we are talking about something in the flask. So what is in the flask with the pH 13? pH 13 is nothing but strong base. Alright. And now you are adding something from the burette and the pH, final pH is around 1. That means from the burette we are adding strong acid. So that's how you can figure it out, whether what are you adding, what is in the burette, what is in the Erlenmeyer flask or in the beaker, whatever the analyte and titrant. So analyte will be in the flask or the beaker, and the titrant will be in the burette, as you know. So we can identify what is the titrant, what is the analyte just by looking at the curve. And here also the equivalence point, when you mark the equivalence point on the y-axis, you can see that is 7. Only difference the curve from 1 and 3, between 1 and 3 is, this is, the first one is just like S shape and the third one is inverted S, just like 2, right? That is the difference. So you know that if it is in the flask, if it is the base, it will be just like a shape 2. If acid is in the flask, it will be just like S. That's the shape. And now let us see how is it different from graph or titration curve 2. You can see the pH when you haven't added anything from the burette, the pH is around 2. That means little higher pH. That means that is weak acid. Where the weak acid is in your flask, that is your analyte. And when you keep adding something from the burette, the pH changes to around 14. That means a strong base is added from the burette. See that just by looking at the curve, you know what is coming from the burette, what is in the flask. And the accurate way to decide by looking at the equivalence point, take the half point from here. When you take that to the y-axis, you can see the pH is 8. That means above 7. That is acidic. So that is basic. Okay, so that is basic. So above 7. Correct? So weak acid, strong base. So that is going to be basic. So that is 8. So the equivalence point is basic, above 7. So we know that is a strong base is added from the burette. So now when you look at the fourth curve here, the titration curve in the fourth one, you can see two S shapes. One here and another one here, right? So if there are two S shapes like that, we can say that is two hydrogen present. We can say that is diprotic acid. That is why you can see two humps or two curves over there. Okay, that's how you can actually analyze the titration curve by looking at it. So you can say whether it is strong acid, strong base, or weak acid, strong base, whether it is diprotic, is it monoprotic, and all those stuff you can actually read from the graph. Okay, so we will see the different parts of the titration curve along with the particle diagram and also how to calculate the pH at different state. Okay, so to begin with, we can see that this is the equivalence point is at 8. So that is for weak acid and strong base. Okay, strong base. That is why it is above 8. Correct? The equivalence point is above 8. And also I can see that is a weak acid because the pH is starting from 2 when something is added from the burette, correct? In the flask, it is weak acid. So in the beginning, how can I calculate the hydrogen ion concentration? How can I calculate Ka? If you know the Ka of the acid, how can I calculate the hydrogen ion concentration for a weak acid? Any idea? For initial point, you haven't titrated anything. So what you have to do is use the formula Ka equal x square divided by concentration of the acid. So that X will give you the hydrogen ion concentration. For the weak acid, we can use this short form. Remember we said that one? Instead of using the rice table, we can directly use this one. So that X will give you hydrogen ion concentration. If you look at the particle diagram, in the beginning, we don't have any base added. All are HA. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules, for example. Okay, so that is just to represent the acid in the flask. Okay, so that is the beginning before adding anything, before adding any titrant from the burette. So when we start adding the titrant, that is the base from the burette, we will reach the early buffering region. So what is a buffer is the combination of a weak acid and its conjugate base. Okay, salt of conjugate base. Okay, so that is buffer. So when we reached that early buffering region, that means when we add few milliliter of the base, the titrant added from the burette, we will still have the excess acid in the flask. So this mixture is going to be form a buffer. So to calculate the pH at this point, we can use the formula pH equal pKa plus log concentration of the conjugate base divided by concentration of the weak acid. And if we look at the particle diagram, we can see that we have still 1, 2, 3, 4, 5, 6, 7 acid. That means excess acid in the flask and few molecules of the acid got neutralized by the base. So we will have the weak acid and the salt of the conjugate base. That forms a buffer. So we can use the buffer formula. The simple formula is concentration of the hydrogen ion equal Ka, concentration of the acid divided by concentration of the conjugate base. And then we have to find the pH as usual, negative logarithm of hydrogen ion concentration. And then we are reaching to the half equivalence point. What happens at the half equivalence point is half of the acid got neutralized by the base. And now we have only half of the acid molecules here, 1, 2, 3, 4, 5. So that means the buffer formula we used, the concentration of the conjugate base and divided by concentration of the weak acid will become 1. So when the concentration they are equal, that equal 1, we can say that pH equal pKa. That's at the half equivalence point. Still it is a buffering region. Still we are using the buffer formula, but only because it is changing to pH equal pKa because the concentration of the conjugate base equal concentration of the acid, because half of the acid got neutralized by the base from the butane. That's the reason. So that's half equivalent point is very important to find the Ka value of the weak acid we used. So if we have an unknown acid, we can find the Ka value from this half equivalence point and we can identify the acid from that Ka value. The half equivalence point we are going to reach later buffering region. So that means most of the acid got neutralized by this time. So we can see very few acid particles left in the flask as shown in the particle diagram. So what happens here? Again, this is a buffering region because we have few molecules of weak acid along with the salt of the conjugate base of that acid, right? So we can still use the formula, the buffer formula pH equal pKa plus log concentration of the conjugate base divided by concentration of the weak acid. So we can use the pH using this formula. Now we are reaching to another important point on the titration curve, which is equivalence point. Equivalence point is where analyte is completely neutralized by the titrant, and the number of moles of the acid is stoichiometrically equivalent to the number of moles of base. So that means we don't have any acid or base. We have only salt and water in the flask. So what we have to do to find the pH, we have to use the same method to find the pH of a salt. So as shown in the particle diagram, you can see that we don't have any acid or base, only salt and water in the flask. And now the last point on the titration curve, which is beyond the equivalence point. So that means we will have more base or the titrant in the flask. So that means what? So we will have POH equal negative log of hydroxide ion concentration because the excess solution determines the pH of the solution. So now here we have the excess base. So first we will find out POH and then we can find the pH as usual. That is by subtracting from 14.